Hey you guys, this is Professor Vitt, and I'm here to just walk you through our next 4 rules of implication. Now, a couple of points here. First things first, the arrow in my Word document actually stands for the horseshoe, and the ampersand symbol here stands for the dot, which is the conjunction function. So the arrow is implication, and the ampersand is conjunction. Just in case you're using the book and it doesn't have those symbols, or you're using a different book and it doesn't make sense, hopefully that's helpful to you. I'm going to go through these 4 rules, and then we're going to work 2 problems, and we'll go from there. So, all right, here we go. The first one we're going to do is the toughest one. It's called Constructive Dilemma. Let me see if I can get this a little bit more zoomed up here. Let me see if I can go to, say, 350. What would that look like? Yeah, it looks a little better. Okay, so here we go. First things first. This looks very complex, but it's pretty straightforward. Here's how it goes. The first line is just a conjunct of 2 conditionals. It goes like this. If it's a cat, then it has worms. And if it's a dog, then it has fleas. It is a cat, or it is a dog, so it has worms or fleas. That's it. That's all Constructive Dilemma says. Next up to bat, we have simplification. Now, I've given 2 forms of simplification here. Your book may not like both of them. It depends on what you're using, but frankly, we don't have time to deal with the niceties. So I've just kind of freed us up a little bit. So simplification just says if you have P and Q, so you have 2 statements joined by a conjunct, then you have one side of that conjunct on its own. You can bring down the P on its own. Likewise, if you have P and Q, you can bring down the Q. Now, some books will require this to occur in a certain order. In other words, they might not allow this second version, but in my class, I allow it because life's too short and you got to live dangerously. Okay, the opposite of sometimes in simplification, I just refer to it as breaking up a happy couple, right? You have a couple together, then you show someone some incriminating texts, and boom, all of a sudden somebody is single again. So that's simplification. Next up, we have conjunction. Now, conjunction is the opposite of simplification. Instead of saying, I have 2 things together and I'm going to put one of them alone, I say I have 2 things alone and I'm going to put them together. So if I have P on a line of a proof and Q on a line of a proof, I can put them together and have P and Q together. All right, next up is addition. Addition is a very, very strong rule. And so the way that it works is if I have P on a line, then I can add P wedge whatever the heck I want. So P wedge Q. This may seem like a strange rule to you. You say, well, can I put anything there? Can I put a not P there? Yeah, you can put a not P there. Why? Well, the way that it goes is, if you remember, the disjunct is very strong, meaning the disjunct is going to be true if only one element of the disjunct is true. And so as long as I know P is true, I can put wedge whatever I want, even if that thing is false. Very often, if you have a conclusion that has a letter in it that does not exist in the premises, you're probably getting it from addition somehow. Now, the second form of addition I'm going to allow, and your book may not allow it, but if you're in my class, you can do it. If you have P, I let you do Q wedge P. Now, really, this is just a combination of a rule that comes later, but for our purposes, we're just going to make this a little bit easier. It doesn't hurt anything. It doesn't violate any of the logic gods' rules. So we're just going to let that fly. All right, so now let's work this next problem. I have not worked this problem. Well, I should correct that. I've worked this problem many times, but I don't remember working it. So if I make a mistake in here, then it's an honest mistake, and you should feel good about the fact that I've been doing this for 20 years and I'm still getting it wrong, right? So let's go ahead and start this proof. Remember, I'm already assuming you know the other 4 rules of implication. So first thing we always do when we're starting a proof, we look for low-hanging fruit. So right here, I'm going to look for something that, maybe would help me out. So I'm going to go ahead and here, I want to get L wedge T on its own, and I see an L here and I see a T here. What that means to me is that I probably have some kind of a, I'm going to use at some point constructive dilemma. Now I'm not sure exactly how that's going to go, but I will figure it out. So let's see here. What can I do first? I could go ahead and combine these two, 1 and 3, but that's only going to get me so far. So why don't we just take line 2 here, and let's simplify line 2. So I've got m implies n on its own right here. That's going to be 2 simp. Right? So all I've done is I've said, look, line 2 tells me that this statement is true. Simplification allows me to bring down one of them, so I have m implies n. All right, now I'm noticing that I have on line 3 n implies t. And then I have on line 5 m implies n. Immediately, you should always ask yourself when you complete one line in the proof, gosh, is there something I can do now that I wasn't able to do before? And in fact, there is, right? If you look at line 5, m implies n and n implies t, we're going to do an example of hypothetical syllogism or high school, what I like to call high school, right? If Mary is talking to Nancy, or if Mary is talking to Nani, and Nani is talking to Tyreek, then Mary's talking to Tyreek. So that's exactly what I'm going to do. I'm going to do Mary. Oops, let's get this underline out of there. Mary is talking to Tyreek. And that's going to be from 3.5 hypothetical syllogism. If you don't know that rule, go back and take a peek at the video. But the basic idea is, look, if m implies n and n implies t, then by necessity m would imply t. That's what I've got here. So now you notice I've got m implies t here, and I've got k implies l here. So what I want to do is I'm going to combine line 1. I'm going to do some parentheses here to make it legit. I'm going to combine line 1 with line 6. And I'm just going to cut and paste line 6 to make it a little bit easier. Boop, 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 boop. Okay, and then remember you have to tell your grader or your reader what rule you used here. And I'm going to tell you I used line 1 and line 6 conjunction. 1, 6 conjunction, right? So all I did here was, this was hypothetical syllogism, and then I combined 1 and 6 onto one line, and then I derived my conclusion, which is L wedge T, from constructive dilemma. And I'm going to repeat what I'm doing here just in case you're watching this going, what? You know, and this is going to be 4, 7 constructive dilemma. Okay, how does that work? Let me talk about this for a second. It'll make a little more sense. Remember, constructive dilemma looks very complex, but it's actually pretty straightforward. Here's what constructive dilemma says. If it's a cat, then it has worms. And if it's a dog, then it has fleas. It's a cat or a dog from line 4, so it's going to have worms or fleas. And that's your answer. That's your proof right there. This proof is hard if you're not yet familiar with constructive dilemma, right? It just will be, because you have to understand immediately that you're going to get this L wedge T by constructive dilemma, so you're kind of trying to build up to getting all the components for that. And unless you see that straight away, it's going to be hard to do. What I would encourage you to do when you're working that proof is exactly what I did. Look for the low-hanging fruit, right? 3 and 5, when you look at line 3, n implies t, and line 5, m implies n, you should be able to see, oh yeah, that's going to be high school. That's going to be high school, right? It's going to be hypothetical syllogism. If m implies n and n implies t, then m will by necessity imply t. Now that you have m implies t, you can kind of look and say, oh, I've got an m here, and I've got a k over here from k implies l, and I combine those, and you can eventually put it together with constructive dilemma. So this was a proof that really tested you on constructive dilemma. So now let's do sample number 2. And let me do let me do a little page break here so that we've got it all together on one line. And I'm going to start off. Remember, I haven't worked this proof for I don't know how long. I don't remember how it's done. This is important to remember when you're practicing proofs, right? Very seldom does someone say, oh yeah, I remember how to do this one. Instead, you go, God, how did I, at least I do, I just go, how did I solve this? And essentially, you're just re-solving it every time you run into it. So let's look at this now. I have in my conclusion S wedge T, and I don't see any, I see an S right here. I don't see any T's, so I'm probably going to get this from addition. I'm just guessing. So my thought is, this is probably going to boil down to me trying to get something like not P and Q, right? So let's go ahead and work this. Let's see what we can get going on. I'm going to go ahead and I'm going to break up line 1. Now, I'm going to only bring down the not M from line 1. I'm going to do it by virtue of simplification. One simplification. If you're working this proof, and you want to bring down the n because you're not sure whether you're going to need it or not, you can go ahead and put it down on line 6. It's not going to hurt a thing. You would just have an extra line in the proof, and there's nothing, you don't get any points taken away for having an extra line in a proof, right? It's perfectly okay. Now, remember, once you complete a step in the proof, you want to stop and take another look at the proof and say, is there something I can do now that I couldn't do before? Well, there is something I could do now that I couldn't do before. I have a not M here, and on line 2 I have P implies M. That would allow me to do a modus tollens. If modus tollens isn't familiar to you, go back and look at that other video. But I'm just going to go ahead and do 2, 5 modus tollens. And the way that this works is the statement for line 2 says, if I'm in San Francisco, then I'm in California. I am not in California, so I am not in San Francisco. And that is just exactly modus tollens. Now, I'm close, but I'm not all the way there yet. If you remember, I wanted to try and get this S. If you weren't able to see that far into the proof yet, it's okay. What you want to do is just try to keep working your premises and shake stuff out. See what comes down the pipe. Well, dun 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 dun. I look on line 3 and I see that I could simplify that. So what I'm going to do is I'm going to take the Q from line 3 and I'm going to break it apart, right? And I'm going to say 3 simp. And that's going to be my rule. Now, you may have an extra line because you also brought down the N. You may have an extra line because you brought down the R and you weren't sure whether you needed it. That's fine. As you work more complex proofs, it's a better idea when you break apart a conjunct to just bring all of it down, because the elements of the conjunct become so complex, it's harder to see whether or not you're going to use it or not. But for now, we're looking pretty good. What I'm looking at now is I wanted to get S wedge T. Well, I don't have a T anywhere in my premises, so I'm probably going to get this by addition. So the proof boils down to getting an S. Well, how could I get an S? If I had not P and Q, I could get an S by modus ponens. And wouldn't you know it? If you look at lines 6 and 7, and I combine them, if I do that, which I'm going to do right now, so that's going to be, 6, 7, conjunction. Now I have the not P and Q that I need in order to bring down the S right here. So then I'm going to bring down my S, and the answer, or I'm going to derive S, and that's going to be 4, 8, modus ponens. All right, I'm almost there. I'm going to derive my conclusion in line 10 from S wedge T, and I'm going to say that's 9 addition. Now, how does this work? Remember, the disjunct is going to be true as long as one element of the disjunct is true. So I know S is true. I can put S wedge not S. I can put S wedge T triple bar Q wedge blah, blah, and just keep on going forever. As long as it's a well-formed formula, it's perfectly legit. Well, here I'm just going to do a wedge T. This allows me then to make my conclusion, and I'm all done. So these are pretty straightforward. These are pretty straightforward applications of the rules. Remember, when you're working these proofs, you're better off working 3 or 4 proofs really well than working 10 proofs and not really understanding much of it. So again, the rule for logic is it's better to work a few proofs really well than to work a whole bunch not so well. And also consistency. For many of you, for me, this was certainly true. You're not born knowing how to do logic. I mean, just few people are. It's an unusual thing, and part of learning is that it's effortful, it's difficult, and so you should feel frustrated sometimes doing this. The key to doing this is not to pound your head into the wall for 3 hours. It's to spend 20-minute breaks, right, or 20-minute blocks, and just come back to it a little bit later. If you do that consistently, over a period of weeks, you will pick up logic, and that's how I found it to be useful to learn these rules of natural deduction. Okay, you guys, I hope that's helpful. Good luck, and please let me know if you have any questions.